Hello, am I audible? Hello, hello. Am I audible?
Yes, sir.
Okay. Is the screen visible? Yes or no?
Yes, yes.
Then who will say that? How come I know whether you can see it or not? You have to answer. Simple. Yesterday we had seen up to this part, right? Second law efficiency we had discussed, which is the ratio of the COP of the VCC and the ideal cycle, that is the Carnot cycle. And we have seen that this area A2 and area 1 have to be the minimum. And that is quite obvious that if I reduce this area, my isenthalpic expansion reaches as close as possible to the isentropic expansion. And this extra part, as the superheated part, also could be reduced. So somehow if I could stop over here and start the isothermal heat rejection, this is isobaric heat rejection, so that is why pressure. If I follow this horizontal line entirely, it will be isothermal, correct? So that way I can execute the process as close as possible to the Carnot, and as such my relative efficiency or cycle efficiency will be, or second law efficiency will be, let's say 90% or anything closer to that of the Carnot, correct? Now we further discuss about the analysis of the same cycle. So my first assumption is Kp changes are negligible. System is stationary, delta E becomes delta U. Okay. So in the first law of thermodynamics, if I apply, what I get is the work part which is related to the internal energy and plus that uh, PdV work. So that including with the internal energy, that gives me the enthalpy part. So the work will be associated as the delta H, correct? Delta U plus delta of PV. So it would be delta H. And here I will see that the work process related to the compression, that is 1 to 2, will be H2 minus H1. Now how do I read this H2 over here? Will be H2 minus HF here, correct? And H1, which is over here, minus HF, correct? HF cancel, doesn't matter. Do you agree?
Yes, sir.
Okay. Now this H2 minus HF is related to, let's say, higher pressure, and H1 minus HF, let's say, lower pressure, means condenser pressure and evaporator pressure, correct? Now my assumption number 2, second assumption, that the saturated liquid line, that means 3F, okay, coincides with the constant pressure line. In the vapor zone, the constant pressure line here, they are naturally like distant away. I can differentiate in them very easily. But in the liquid zone, being the incompressible one, the pressure effect is very, very negligible. So what I mean to say is the pressure line like this for higher pressure and lower pressure line like this. I mean to say condenser pressure will be something like this and evaporator pressure something like this. They are very close to the saturated line. Do you agree? Any problem to anyone in this assumption?
No, sir.
And this assumption is valid for the subcooled region. Why? Because it is liquid and liquid is incompressible. So whether the pressure is 1 bar or 10 bar, it's an incompressible one. Correct? So effect of pressure is negligible as such. So condenser pressure line like this, evaporator pressure line like this, and the saturation line, they're almost like the same one. Okay, valid with this assumption, fine. Any doubt to anyone?
No, sir.
Okay, so now we are focusing for this work part and this work part. This is a triangular one, this is a rectangular one. We will try to prove that it is one and the same. So how do we do that? So second law of thermodynamics, TdS is equal to dH minus VdP. ये plus PdV होता है if it is a compressible one, it becomes minus or VdP because it is incompressible liquid part. Correct? And further, you are keeping the pressure constant for the condenser pressure. That means this, here, and here. There is a constant pressure, so dP is 0. And what I get is only dH. And the value of dH I know. Correct? So I would say H2 minus HF. H2, then 2 dash, then 3, and then F. H2 minus HF. Correct? Is what that area is E2, 2 dash, 3, F, then G, and then E. Do you agree? Area under the curve. Any problem?
No, sir.
Okay. And for this reason only, this purpose only, we defended with the assumption that the constant pressure line is slightly here and this saturated line are very close to each other and we can make it as approximately same. So we are using or implementing that assumption over here. Otherwise, I have to do it something like this. Very small change in the pressure line deviation towards the left hand side. We neglect it. And I can directly say for this 3FG. Otherwise, on some constant pressure line, condenser pressure line, it would have been over here something, F dash. Are you getting it?
Yes, sir.
So constant pressure line and saturated line, we are assuming to be very close to each other. So difference is negligible. And as such, we can say that it is following the same saturation curve. Now, similarly, this is H2 minus HF. I can find H1 minus HF. So for that, it is E1, then F, G, E. Correct? Area under the curve. So saturated vapor minus saturated liquid. H1 is basically Hg and HF. Agree? In doubt?
No, sir.
So now what remains with me, if I do the subtraction H2 minus HF and H1 minus HF, then what remains with me is this here and here, correct? Do you agree? I will show with the number 1, 2, 2 dash, 3, F1. Correct? Iska or iska difference?
Yes, sir.
What you will have is this 1, 2, 2 dash, 3, F1. Do you agree?
Yes, sir.
And what is that? 1, 2, 3, F1. Correct? 1, 2, 2 dash in between, 3, F1. That is the difference. So this is the work done. Correct? And work done is related to Q rejected and Q absorbed. ये cycle है. Cyclic integral of work is cyclic integral of heat transfer. Delta U is 0. First law. Q minus W. Delta U is equal to 0. So delta W is delta Q. So net work in BCC is the Q rejected, that means condenser, minus Q absorbed, that means evaporator. So that is nothing but the same 1, 2, 3, then 4, 4 dash, okay, then C, D, 4, 1. This we have already seen. here, VCC. Correct? Yesterday. So that is the same thing I'm repeating over here.
Yes, sir.
So now if I say that this and this is the same, sorry, here is the same. So 1, 2, 3, F1 is as same as 1, 2, 3, 4 dash C, D, 4, 1. If they are same, that means this area A3 is as same as A2. Do you agree? Any problem? Am I audible?
Yes, sir.
So then you have to give me the answer, otherwise I will stop over here only. How can I proceed unless you tell me whether you are clear or not? That is your job, not my job.
Yes, sir. Yes, sir.
Yes, sir.
If I ask you the question, is there any doubt? Then either yes or no. Those who will be having some doubt, they will ask. Those who will not having any doubt, they will say no.
No, sir.
If I ask you clear, then you have to say clear or not. If you are not clear, tell me, I will repeat it. If you don't say anything, I cannot proceed ahead. Loss is yours. See, is this clear? How area A2 is equal to area A3? Any doubt to anyone in the entire class?
No, sir.
No, sir.
Okay. Now this example is the implementation of whatever we had learned as far as this Carnot cycle and VCC is concerned. Okay, so assume a Carnot cycle operating between the same temperature and then determine. So I leave this to you as a kind of homework. You can do it at your home because this is related to the TS part, not the pH one. pH chart you have, TS you can draw anytime because you have the table, correct? So all these equations you can read the values from the table and cross check. Okay, no need to waste the time over here. Right? So what I was trying to emphasize on is this, the second law efficiency. So now you know about A1, A2, A3, etc., etc. You can cross check about the value, and here we can say that it is 80% deviation with respect to the corresponding Carnot refrigerator. So whatever is the COP of your VCC, that indicates that there is a 80% deviation with respect to the performance of the Carnot corresponding Carnot refrigerator. If you could operate a Carnot refrigerator between the two temperature limits, whatever is the performance, 80% of that will be given by this VCC. So this is how you compare about the Carnot cycle and the VCC. So what is our job is to put this A3, A1, A2, because basically A2 and A3 is same. A1 is that superheat part. Right here also I had written A3 4.43, A2 also 4.43. So to keep this as small as possible, that will give me uh, like approximation towards the Carnot cycle. Fine. So you can open the chart for which is this refrigerant 12. Okay. So R12. The slides are anyway shared with you, so you can open the chart and read the values of entropy. Basically, what you need is the entropy. And here entropy. Fine. So that you can read from the table. Okay, and
Yes, sir.
cross check. That is a kind of homework. I don't want to waste the time over here. You have enough practice how to solve the numericals. A multi-stage vapor compression cycle. Why do we need multi-stage? So basic purpose is to overcome the limitations. Now, what are the limitations of the single stage? Let us deal with that. At the low evaporator temperatures. Okay, that means basically pressure is also low, correct?
Yes, sir.
So if I have a inlet temperature of 1 bar and exit temperature of say 15 bar, okay, that means evaporator pressure, whatever is 1 bar, and condenser pressure as 15 bar. Then the one stage, this much compression in a single stage naturally will drastically reduce the volumetric efficiency. And compressor is done. Oh yes, I was supposed to send you compressor notes, right?
Yes, sir.
Yes, sir.
CR जरा मला नंतर थोड्या वेळाने आठवण करून द्या माझ्या डोक्यातनं जात नाही
Oh, sir.
to share the compressor notes. I will share this. So volumetric efficiency, the pressure ratio increases. Finally, it is the function of the pressure ratio, correct? 1 plus K minus K times P2 by P1 raised to 1 by N. So the volumetric efficiency reduces because of the pressure ratio. Higher the pressure ratio, volumetric efficiency is less. So why to go for such a heavy pressure ratio, 1 to 15, in a single stage? Split it. So that is why we go for multi-stage. Second and major aspect is the compressor staging. The moment you get deviated from which is the ideal compression process, minimum work. What type of compression process is there which offers minimum work? ये तो गैस टरबाइन में हो गया होगा.
Adiabatic, right?
No. Diabetic will have more work. Yes.
Isothermal process.
Isothermal compression process that requires the minimum work. A diabetic will naturally take maximum work because you are not allowing any heat transfer. Okay, so isothermal compression process is the ideal one. Ideal in the sense minimum work requirement. So the moment you start getting deviated from the isothermal one, that means you need cooling. Correct. So that is why if you go in a single stage for let's say the adiabatic compression, then the deviation with respect to isothermal compression will be too large. So what we do is multi-stage. So slight deviation, cooling karo close to isothermal. Again slight compression, slight deviation with respect to isothermal. So cool, get back to original. ये ऐसा कुछ हुआ है, सिखाया है नहीं सिखाया?
क्या, sir?
Isothermal compression, multi-stage, compressor part.
नहीं सर, ये सब इतना डिटेल में नहीं सीखा है.
नशीबच फुटकल तुमचं, थांबा जरा. आता या कॉम्प्रेसरच्या स्लाइड्स मला वाटतं हा. Is the screen visible?
Yes, sir.
So we use air intake, LP cylinder, then there is an intercooler, then intermediate pressure cylinder, then again intercooler, and then the HP cylinder. Now why do we need this? The intercooler is compressed air is cooled between the cylinders. So iska outlet and iska inlet. We cool it in between and bring it back to the original condition in terms of temperatures or the intake. Pressure naturally will be higher. It's just rejecting the heat, not expanding. Correct. So final delivery temperature would be at the lower value. What I want as the final one. If I do not have any intercooler, let's say this is 27 degree. After compression, 100 degree. Then second compression, 200 degree. Over here, 300 degree. I do not want that because that is direct exergy loss. So what I do, 27, let's say 100. Bring it back, 27, 100. Bring it back, 27, 100. Are you getting this?
Yes.
So because of that, your internal energy also reduces. If the temperature is lower, internal energy is less. It's a air to be treated as ideal gas. Correct? Internal energy is CVDT or CV into T. Enthalpy is CP into T. Now, if the internal energy is less, so that means my input required work is also less, and that is what is I want. Unnecessarily compressing at the higher pressures and higher temperatures naturally will require much more work. So if I reduce the temperature 2700, why it is required 100 and 200? I will bring it back to 27. Correct? So again 2700, again bring it back to 27. So pressure increases, temperature doesn't. So that is why this size is larger, this is intermediate, this is smaller. Because the pressure is already built up. But you don't want the temperature to be high. Do you agree or not?
Yes.
This is the discussion which I was telling. Let's say this is your isothermal compression process. It would reach at 9. PV is equal to constant. Now what you do? Kisko le lo. You reach to 4 if with the adiabatic one, PV raised to, or let's say polytropic compression. Okay, isothermal one you would have reached over here 2. But because of the polytropic compression, let's say you reach to 4. Then what do you do? Intercooling. Reduce the temperature. Pressure remains same, only temperature reduces. Then further, you compress isothermally, you can reach to 9. But now you are following the polytropic line, you reach to 3. Then again 3 to 9. Second intercooling. Then again third stage. So this is how you save this work. Are you getting it? अगर ये intercooling नहीं होता तो you
Yes.
would have followed 4 to 5. Isothermally, you could have reached to 9. Without intercooling, here you could have you reached to 5, and with intercooling you reach to 3. So at least this 3 5 means 2 4 5 3. इतना तो वर्क बच गया ना.
Yes.
Yes,
And
sir.
compressor is something on which you have to do the work. जब खर्चे की बात आती है तो कम से कम, फायदे की बात आती है तो ज्यादा से ज्यादा. So for the turbine which gives us the power, we want it maximum work. For the compressor where we have to do the work, it has to be minimum work. You agree or not?
Yes, sir.
Yes, sir.
तो ये सब नहीं सिखाया.
No, इंटरकूलर का सिखाया था, लेकिन ऐसे जो प्रोसेस रहता है ये सब नहीं सिखाया था.
तो फिर क्या सिखाया?
If numericals में we use this for gas turbine, that is.
Yeah, but what is the logic for intercooling? Why do you want intercooler? That is basically to save the work. You cannot execute a isothermal process, isothermal compression. It will take hell of a long time, correct? At every single instant,
Yes.
compression and then heat rejection. Further compression, heat rejection. Who will wait for that? Your motor is running at, let's say, 1440 RPM. I cannot wait. So I
सर
provide
हमको
this.
ये ऐसा मतलब गैस टरबाइन में इंटरकूलिंग करके सिखाया था और ये बताया था कि मल्टी
Intercooling, reheating, and regeneration.
रीजनरेशन।
हाँ,
Yes, sir.
तो ये बताया था और एक और स्टेटमेंट दिया था कि हम लोगों के एकदम सबसे एक्सट्रीम केस में सिर्फ दो ही स्टेज है, मतलब मल्टी स्टेज नहीं, दो स्टेज में ही इंटरकूलिंग होगा और उसमें भी इंटरमीडिएट प्रेशर का बस एक फॉर्मूला बोला था, वो ज्योमेट्रिक मीन हो जाता है
हाँ, अंडर रूट
एरर।
ऑफ P1 P3
हाँ,
P2
फॉर
is equal to under
मैक्सिमम
root of
वर्क
P1.
आउटपुट, बस इतना ही
कहाँ
सर।
से आया वो?
सर वो बस बताया था ऐसा, मतलब वो मैम ने शायद डिफरेंशिएट करके कुछ बताया था शायद फॉर्मूला, वो वर्क का लिख के फिर हम जब डिफरेंशिएट करके आता है। हाँ
Here it is.
हाँ, सेम गोज फॉर वो हायर, मतलब उधर भी गैस टरबाइन में भी जो रीहीट साइकिल है उसमें भी जो इंटरमीडिएट प्रेशर है उसके लिए भी यही फॉर्मूला है, बस ये सब बताया था सर।
Same. Turbine में भी same ही है. Compression is the reverse process of turbine. There is expansion, here
Yes,
it is
sir.
compression.
क्योंकि सर वो कैसा था सर, बहुत लिमिटेड टाइम था गैस टरबाइन पूरा पढ़ाने का, तो मैम ने बताया था, डिराइव किया था एक आधा फॉर्मूला, बट ज्यादा फोकस न्यूमेरिकल कैसे सॉल्व करना है और क्या कैसे अजम्पशंस लेने हैं वो सब। मैम ने भी अज्यूम ऐसा करके बोला कि कंप्रेसर पढ़ाए।
Let me share the presentation right now only. Very surprising thing. Here I have to first of all attach. Those who are preparing for GATE, you have to know all these things.
सर कल जो एनटीयू का बात कर रहे थे सर, वो भी नहीं पढ़ाया हमें।
वो तो हीट ट्रांसफर में है, वो तो होना चाहिए।
नहीं सर, वो भी मतलब से एलएमटीडी पढ़ाया था, एनटीयू बस बताया था कि एनटीयू होता है।
तो राहुल को कैसे पता है?
सर वो भी गेट का प्रिपेयर कर रहा है एनटीयू
मैं
का।
जिंदगी में जितने स्लाइड्स बनाए ना सब दे देता हूँ आपको।
हाँ सर वही, एनटीयू नहीं पढ़ाया था सर, और रेडिएशन में भी सिर्फ वो जो 12th स्टैंडर्ड वाला रेडिएशन है वो पढ़ाया था।
12th स्टैंडर्ड वाला रेडिएशन क्या होता है?
वही सर, वो लैम्डा टी, लैम्डा मैक्स टी इक्वल्स टू कांस्टेंट।
Stephen's law जो
हाँ,
है।
स्टीफन
वाइज
गोल्ड।
डिस्प्लेसमेंट लॉ सिखाया?
बस हाँ, विंस डिस्प्लेसमेंट, बाकी सर व्यू फैक्टर और इरेडिएशन ये सब
हाँ,
बस।
शेप फैक्टर, व्यू फैक्टर
नहीं, शेप फैक्टर तो नहीं सर, सिर्फ इरेडिएशन का फॉर्मूला बताया और उसका वो इंटीग्रल बताया, बस हो गया। वो ऐसा शायद ऐसा था कि पैंडेमिक में इट इज डिफिकल्ट टू फॉर द स्टूडेंट्स टू
घंटा।
अंडरस्टैंड, ऐसा कुछ रीजंस थे सर मेरे।
पेंडेमिक में तो उल्टा आप भी अपने घर पे, हम भी अपने घर पे। How many students are there for preparing for GATE?
है सर अच्छे खासे, मतलब होंगे
तो
सर।
टेल मी, बाकी आपको कौन से थर्मल रिलेटेड है, बाकी कौन से नोट्स आपके पास नहीं है जो प्रॉपर्ली नहीं सिखाया? आई विल शेयर इट और एटलीस्ट आई विल ट्राई टू अरेंज।
सर एक तो रेसिप्रोकेटिंग कंप्रेसर्स का हो गया,
वो मैं भेज रहा हूँ अभी।
फिर वो एनटीयू का जो कल था, मतलब हीट एक्सचेंजर का।
हाँ, ओके।
फिर
हीट एक्सचेंजर टॉपिक हुआ है,
हीट एक्सचेंजर हुआ है सर,
कंडक्शन
एलएमटीडी
हुआ,
भी पढ़ा है,
कन्वेक्शन हुआ, रेडिएशन
कंडक्टर।
हुआ,
हाँ
और हीट एक्सचेंजर में सिर्फ बेसिक पैरेलल, काउंटर, क्रॉस।
काउंटर और उसका एलएमटीडी का फॉर्मूला और उसके न्यूमेरिकल्स ही कराए, मतलब इफेक्टिवनेस और वो वाले क्वेश्चंस नहीं किए हम लोगों ने एनटीयू के।
अच्छा, ठीक है।
फिर और सर और तो नहीं सर, मतलब बाकी तो सर आपने ही पढ़ाया ना।
मतलब बाकी कोर्सेस
हाँ,
इन्होंने
मतलब थर्मो में ही आ
लिए।
जाए ना सर बाकी सब तो।
फ्लूइड मैकेनिक्स, थर्मोडायनामिक्स एंड हीट ट्रांसफर। फ्लूइड मैकेनिक्स तो हुआ होगा अच्छे से।
हाँ, फ्लूइड मैकेनिक्स में सिर्फ सर रेसिप्रोकेटिंग कंप्रेसर नहीं पढ़ाया था सर ने, फ्लूइड मशीन्स में। तो वही सर, वही मैं मानूं, वही आपको बोला। बाकी तो सर ने सब पढ़ाया है, मशीन्स और
ये देखो भेज दिए, मिल गए।
क्लासरूम में डाला सर?
Classroom. One is compressor, the other is compressor example. Two files are there, so you can have the solved numericals also.
ये
मिला?
सब हाँ सर, बाकी तो सर आपने पढ़ा है ना सर, मशीन्स भी हो गया, रंकाइन साइकिल।
नहीं, I'm saying other than thermodynamics, fluid mechanics भी हुआ होगा अच्छे से.
हाँ सर,
And heat transfer.
हाँ सर,
IC engines.
आईसी इंजिन्स तो अच्छे से हुआ था सर, बस वो गैस टरबाइन मैम ने थोड़ा कम पढ़ा, मतलब बेसिक्स तो सबको ही पढ़ाया था, मतलब सब कुछ कि क्या कैसा है, कौन से जगह क्या कर रहे हैं, बस मैम ने एक बात बोली थी कि कंप्रेसर तुमने पढ़ रखा होगा ऐसा,
अच्छा, हाँ.
बाकी कुछ नहीं, बाकी सब पढ़ा है।
तो गैस टरबाइन चाहिए?
नहीं
वो
सर,
आता है.
मतलब गैस टरबाइन अभी हमें तो सर आता है, मतलब बाकी लोग का मेरे को नहीं मालूम सर।
नहीं, गेट वाले लोगों को.
हाँ सर, हमें आता है।
हाँ, तो बेसिक 3 मेथड्स हो
मैम
तो
ने भी
मैम
मैम
ने
ने
वो
भी
दिया
पढ़ाया
होगा.
है।
हाँ, वही रीजनरेशन.
हाँ सर, मैम ने अच्छे बड़े न्यूमेरिकल्स भी लिए, मतलब तीनों के साथ, और प्रेशर का भी लॉस हो रहा है वाइल,
अच्छा.
वो सब भी लिया है सर, बड़े न्यूमेरिकल लिए।
हाँ, तो ठीक है. कंप्रेसर भेज दिया. आई विल ट्राई टू फाइंड फॉर दिस
एनटीयू का,
इफेक्टिवनेस एनटीयू.
हाँ
इफेक्टिवनेस
बाकी
एनटीयू
सर,
आई विल सर्च.
बाकी सर, बाकी तो इसके बाद सर सब इसके बाद वेपर अब्जॉर्प्शन में तो सर सब नया नया कॉन्सेप्ट है ना सर।
वेपर एब्सॉर्प्शन आपको गेट में है क्या, या वेपर
नहीं
कॉम्पैक्ट?
नहीं है, मतलब हम नहीं पढ़ते, मतलब वो बहुत रेयरली कभी पूछा भी नहीं है उसके बारे में।
क्योंकि वो जनरली यूनिवर्सिटी स्ट्रक्चर में भी वो लास्ट सेमेस्टर में होता है.
हाँ,
तो गेट में होगा नहीं होगा उतना
नहीं सर, सिर्फ
कवर.
बीसीआरएस तक ही पढ़ते हैं हम लोग, बेल कोलमन साइकिल और बीसीआरएस पढ़ते हैं, और साइक्रोमेट्रिक।
Psychrometry, oh, it will take time for me to start because I have to
यस सर,
finish refrigeration part.
यस सर, यस सर।
Before MST refrigeration, after MST psychrometry.
बस सर ये अपने ये वाले टॉपिक से सर इतना ही हम लोग पढ़ते हैं, मतलब
कौन सा वाला टॉपिक?
मतलब रेफ्रिजरेशन और एयर कंडीशनिंग से।
अच्छा, ठीक है. Let us resume back. Is the screen visible?
Yes.
Yes.
So this is the point I was talking about. Compressor staging करोगे, and if you provide the vapor intercooling or gas intercooling, whatever you call, air intercooling. Okay, to reduce that excessive discharge temperature, you don't want the temperature. You want basically the higher pressure, not higher temperature. Correct. If you execute the isothermal process, temperature will be as same, inlet and entry. If you do not allow for any heat transfer, then T2 by T1 is equal to P2 by P1 raised to gamma minus 1 over gamma. Very high values. But do we really need such high temperature? No. So that is why we should go always for the multi-staging part. Okay, ये college तो open है from today for us and for those who are interested. So you can, those who are at least staying in Mumbai, they can come to the college. I can show you about that compressor experiment also. It's a very simple one. 5-10 minutes में हो जाएगा. How the intercooler affects. I can show you practical also. Fine. So now coming back to this. So if you reduce the compression work, then naturally your COP increases, correct? Refrigeration effect remains same. Compression work reduced because of multi-staging. So what is the ultimate effect? Increase in COP. So multi-staging always helps for increasing the COP, better COP. Do you agree?
Yes, sir.
Yes, sir.
So there are different techniques or different methods through which you achieve this multi-stage. So let us deal with this. You observe this pH chart. Now you are familiar with pH chart, so I need not worry about that. Okay. Let's say we start over here, 1. Okay, first stage compression. So I'll show it over here. LP compressor 1 to 2. Okay. Then I go for this intercooling. So the temperature is reduced 2 to 3. So here it is 2 to 3. Agree? Now there is a further part 3 to 4 which we call as the flash intercooler. अब ये होता क्या है? Next slide. Let us first complete the cycle. Okay. So here it reduces from 3 to 4. So exit condition is 4 over here. Okay. Then 4 to 5 is my second stage HP compressor, high pressure compressor. Okay. Then 5 to 6 is my condenser. Then 6 to 7 is the first expansion, first throttle. So I put it like this. And I deliberately connect it to the same flash intercooler. Why? That you will understand after the next slide. Okay. Then this is my 6 to 7. Then this 7 to 8 happens in between. कैसे होता है बाद में बता रहा हूँ. Okay. So my condition at exit is 8. Then 8 to 9 is the second expansion. And 9 to 1 is my evaporator. This completes the cycle. Any difficulty in the cycle?
No, sir.
Okay. Now this, let us try to analyze this. This is restricted for ammonia and R12, very typical for that. Not all the refrigerants are suitable for this kind of arrangement. Reason being the working principle of the flash intercooler. So let us see how this flash intercooler works. Cycle also. So this is a tank, okay, very similar to your Venturi. Not Venturi. What do you call Venturi? जो IC engine में होता है. What do you call that? Throttle position. That V shape, Venturi shape. उसको क्या बोलते हैं? Air fill mixture. What is the name? I forgot it.
Carburetor.
Carburetor. Yes, exactly. That is a Venturi shape, correct? You open the throttle accordingly, so as to get higher amount of
Yes, sir.
fuel or lower amount of fuel. So the fuel tank is always filled with the fixed level. It's very similar to that. There is a fixed level, okay, and this is maintained with the float valve. There also you maintain with the float valve, correct? The float valve ऊपर
Yes,
हो गया
sir.
तो
Yes, sir.
fuel gets spilled out. So same logic, same principle applied over here also. Okay, so this float valve serves as the expansion device. It's a preset value. If it goes beyond that, expansion. Fine. Now, what is this expansion? That is related to this 7 to 8. Okay, because of this float valve, which is acting itself as a expansion device. Now, what happens across this entire system? 3 is the inlet, 4 is the outlet, 7 is the inlet, 8 is the outlet. Do you agree?
Yes, sir.
Yes.
2 inlets and 2 outlets. Okay. Now observe the situation. 3 is the vapor part, 4 is also the vapor part, 7 is the liquid part, 8 is also the liquid part. 3 is vapor part, 4 is vapor part, 7 is liquid part, 8 is liquid part. Agree? Liquid matlab liquid plus vapor. And this is liquid.
Yes.
Correct? So the balance, mass balance and energy balance also, of course. The liquid part after the throttling. My first throttling is 6 to 7. So 7 is a liquid plus vapor mixture. Out of that, the liquid part is expanded to saturated liquid, that is state 8. I think I should have shown this diagram. Liquid plus vapor. Okay, this gets expanded. So because of that dryness fraction, that is vapor part, and the liquid part over here, that gets expanded and reach up to this part. Same over here, like this. Heat rejection, condenser, it comes to 6. Similarly over here, heat rejection, it comes to saturated liquid. Correct? So it reaches to 8. Okay, through this float valve, because it has to maintain the liquid level. And the vapor part goes to the compressor. Vapor part goes to the compressor. 4. Do you agree? So 7, which is the liquid part, partially, liquid plus vapor part, partially split. Cooling will give me saturated liquid, and vapor will go here. Vapor को कोई problem नहीं. Now, who will offer this cooling? here 3 is also rejecting the heat, तब जाके 4 पे होगा, correct? So here there is a heat rejection 3 to 4, which is sensible heat rejection. 7 to 8 is a latent heat rejection, and total of this is a 7 to 4 vapor part as the latent heat addition. Do you agree? I repeat it. 3 to 4 sensible heat rejection gas, 7 to 8 latent heat rejection liquid, and 7 to 4 is the latent heat addition for the vapor part. 7 is the mixture, liquid plus vapor. ये liquid rejection है, vapor addition है.
Yes, sir.
So that is what is written over here. The vapor part goes to HP compressor. You have to reach from state 7 to state 4. Correct? So who will do that? So the energy balance, if you try to write down, then that is 6 to 7. Sorry, 7 to 8 liquid cooling, 3 to 4 gas cooling is equal to 7 to 4 vapor heating. 7 to 8 liquid cooling, 3 to 4 gas cooling is equal to 7 to 4 gas heating. Are you clear? Any doubt to anyone?
Yes.
So the vapor flash through this flash intercooler. Okay, so this is more like a flashing bubble, like where phase change is taking place. Heat rejection and phase change. Pressure is constant. You can observe in this pH chart, say 8, 7, 4, 3, everything is on the same pressure. Agree? No pressure change. It's only the heat rejection and heat absorption part. Okay? So 3 to 4, vapor is flashed through the intercooler. Sensible heat removal, 3 to 4. We discussed it. Latent heat removal, 7 to 8. Liquid part is equal to the latent heat added for the gas, that is 7 का gaseous part goes to 4. So अपने आप तो नहीं जाएगा ना. So 2 heat rejection processes and 1 heat absorption process. Heat addition process. Fine. Now throughout this process for 874, 3 is superheated, you know, but 4 is saturated. So 874 is constant temperature. Correct? So liquid at the intermediate pressure expanded to saturated liquid. This is like a two-phase part. No? 7 is two-phase part after the expansion inside the door. So certain part goes to saturated liquid. Remaining part will absorb that heat and goes to saturated vapor. Saturated vapor means 4. Saturated liquid means 8. Saturated liquid is 8. Saturated vapor is 4. Agree?
Yes, sir.
And the latent heat removal due to the expansion, that is this saturated liquid process 7 to 8, means two-phase liquid part to saturated liquid. So that is a latent heat removal. Here, what this I am talking about, 7 to 8. This is latent heat removal. Then sensible heat removal 3 to 4. दोनों का addition is equal to that heat, same heat added for the gas. So the energy balance is like this. Accordingly, you have to adjust the mass balance. So how much mass is to be expanded, how much mass is to be in the liquid phase, how much mass in the vapor phase. So dryness fraction plays a very, 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 very important role. Okay, this is called as the flash interval. Liquid flashing is more like एक टब इमेजिन करो filled with water और उसके बॉटम में एक लेट्स से पाइप, ओके, गार्डनिंग पानी डालने का पाइप, एंड यू परफोरेट इट एंड पास द एयर. तो जैसे जैसे एयर बबल्स ऊपर आएंगे, दैट इज समवट सिमिलर टू अ फ्लैश इंटरकूलर. So air resembles to our steam, which is at, or steam नहीं क्या बोलेंगे, high pressure, high temperature, gas, refrigerant vapor. So that is at the higher enthalpy value, so it will reject it. That is the sensible heat removal, 3 to 4. The bubble collapses, liquid part, vapor part. Okay, boiling condensation, वो तो आपका हुआ नहीं होगा ना, heat transfer same 5.
हाँ सर.
हाँ मतलब हुआ है, वेरी गुड. So you know nucleate boiling, pool boiling,
नहीं ये सब नहीं पता सर.
है? तो क्या हुआ है? Slug boiling, pool boiling, annulus boiling.
नहीं सर ये कुछ नहीं हुआ है.
हे भगवान, जाने दो. Now this example is just to give you the glimpses. You can solve it if you want at your home. I'm not going to ask such kind of question in the MST or ESC. This is just for your what I can see, conceptual clarity. You read the pH chart for ammonia for the given values of pressures 1.4 bar and 10 bar. You can cross check the values if you want, and you can find out about the mass balance and the energy balance. Okay, heat and mass balance, which is important over here. You can have that value over here. So all those values over here, and you can cross check heat balance, mass balance. So this is just for you to give that idea. I'm not going to ask any such question in neither in MST nor in ESC. Okay, so just to make an impact on your mind. So if you do not use, without any intercooling, your power requirement is 289, and with intercooling, means flash intercooler, I'm not talking about the compressor part, flash intercooler, then you save around 140 kilojoule per minute, correct? 890 and let's say 750. So 140 kilojoules per minute could be saved. So naturally your power requirement is reduced. That means your COP is increased. Agree? This example is just you imbibe on your mind about the importance of flash intercooler. Fine. Should I move ahead?
Yes sir.
Okay. Now, if I use such kind of system, then what are the disadvantages? The liquid refrigerant in the tank here is at some intermediate pressure value, correct? And it is a liquid part, so saturated liquid. We do not offer for any subcooling or anything, correct? Now, what happens practically? If some heat is absorbed in this liquid line, तो वो liquid saturated नहीं रहेगा. That liquid is like evaporates. Correct? Before the expansion valve itself, what we have designed the expansion valve is the saturated liquid start. Subcool किया तो very good. The expansion device is developed, capillary tube or solenoid or whatever it is developed in a sense that the start point of the expansion is the saturated liquid. But if your liquid would absorb some amount of heat and goes to some two-phase part, then your expansion is not as per the theoretical expected part. So this becomes the operation of the expansion valve becomes sluggish. Why? Because your differential is reduced now. Entire liquid to liquid plus vapor. Now it is on already liquid plus vapor to liquid plus vapor further part. So the time required would be much more because from the beginning itself it has to deal with two phases. And we have not designed the expansion device for two phase at the beginning. We have seen in the theory, either we can assume for the saturated liquid part or even the subcooled. So that means it is a pure liquid only. Saturated or subcooled, but it is liquid only. We do not design the expansion valve for the two phase at the beginning. At the exit, it is by default. But the expansion has to start from the liquid phase only, saturated or subcooled. No vapor. So then naturally, functioning of the expansion valve becomes a sluggish one, late. And that poses the problem. So here this entire chamber, I can say, is like a open thing, na? Because it is more towards the phase change part. It's not like one compartment to second compartment, heat transfer, sensible, nothing like that. Entire is the latent part. So if anything happens over here and the liquid absorbs the heat and goes to two phase part, then state 8 will not be a pure liquid. Correct? It will be something like state 7 only. Liquid plus vapor. Then your differential is reduced and the operation becomes sluggish. So that is the main problem. So what we do? Change it to a totally separate part. We call this as a shell and coil intercooler. See here how much time left?
So 5, 6 minutes.
So I will finish this only. Simple now. Baki cycle same. 3 vapor part. Okay. Here there is a liquid. कहाँ से आया? This condenser part. This 6 directly comes over here. So this is liquid only. Do you agree?
Yes, sir.
Let's say certain part, certain fraction is expanded. So this is liquid plus vapor. So vapor part from here will go directly here. And the liquid part over here will absorb the heat in this heat exchanger. Do you agree? And comes to the expansion valve. Let us discuss now over here. This part as it is, same. Do you agree? इसमें कोई problem नहीं है.
Yes.
So this 6 to 7, first part, that is also as 7. Now what I get over here is the liquid plus vapor part. Correct? This will serve here as a pre-cooling one. Vapor goes this way and my entire expansion from this 6, ये liquid ये 8 and then 9. So this vapor part 7 plus 3, matlab what I can say, gaseous plus the two phase. That will go over here 4 as it is. 7 wala and 3 wala will come at 4. Okay, but what I achieve out of this is at a lower pressure, state 7. So naturally temperature is also reduced, correct? Iska corresponding saturation temperature, let's call this as 7 dash. So 7 dash temperature and 6 temperature are naturally different. 6 temperature is a higher side. Condenser pressure is higher, so naturally
Yes.
saturation temperature is higher. 7 intermediate pressure is lower, so its saturation temperature is also lower. So this what I can say, reduced temperature liquid serves for the pre-cooling. After that, it will absorb the heat and expansion. So here my expansion is not 6 to 7 and let's say 7 dash to 9. Not two stage. Expansion is single stage, 8 to 9 directly. This is only pipe. This is only pipe. Okay, this is also only pipe. Expansion is between 8 to 9 directly. Why pressure at 6 and pressure at 8 would change? No expansion, it is just the pipe flow. So my expansion is directly for the higher pressure range, and that too with the subcooled part. And we know because of subcooling, naturally the refrigeration effect is increased. So better to have that subcooling effect, better to have the higher pressure differential. So here there is no bubble part. This is a pipe, this is entirely filled with the liquid. लिक्विड कहाँ से आया? 7 का लिक्विड पार्ट. गैस कहाँ से जाएगा? 7 का गैस, 3 का गैस. And this 7 का liquid serves, this liquid serves as the pre-cooling for 6 to 8. So here also the same liquid refrigerant, here also the same liquid refrigerant, but at 7 it is at the lower pressure, intermediate pressure liquid. At 6 this is the high pressure liquid. Are you getting it clear? This is high pressure liquid, 7 is intermediate pressure liquid. Naturally temperatures are different. And that serves as the pre-cooling. Any doubt?
No, sir.
Okay. This is generally employed for ammonia. Okay. The advantage, it subcools the liquid, it eliminates that flashing part ahead of the expansion valve. तो यहाँ पे कोई heat transfer की गुंजाइश ही नहीं है. This is at the same pressure and even subcooled, तो heat का सवाल ही नहीं. It is getting cooled and large pressure differential for this expansion 8 to 9 because it is condenser pressure to evaporator, nowhere that intermediate pressure coming into picture. The only limitation is that it is not possible, practically of course, theoretically सब कुछ possible है, to intercool the liquid as much, means quantity wise, quality wise नहीं, quantity wise, as that in the flash intercooler, because over there you have the entire control of the heat and mass balance. Here there is no mass balance, they are separated. The only thing which you can play with is how much fraction you can take out over here. Let's say this is 100. So whether it is 50-50 getting diverted, 60-40, whatever it is. So lower control on the intercooling part. Mass of the intercooling liquid means 7. That is the only limitation. In the flash intercooler, everything is open. So you can maintain the mass balance and energy balance very easily. Here, energy balance is a function of the mass balance itself because your mass is not free. It's a cycle. Nowhere mass coming in, nowhere mass going out, extra part. You have to play within the same. So that poses the limitation. Fine. So we'll stop over here for today. Time gets over. Any doubt to anyone?
No, sir.
Okay. So I will try to find out some good material from my own notes related to that heat exchanger, means what you call epsilon effectiveness into method that I will share with you. Okay, by the way, क्या हो गया lab का? Have you plotted? Have you seen the nature of the chart? Effectiveness versus mass flow rate. Oh, basically delta T versus mass flow rate. You have to do that. After that only I will share the write-up, because once I share the write-up I have to give some deadline. फिर बाद में मत बोलना कि ये किया नहीं है. Okay, show me that graph in the next lecture so that we can finalize everything. Okay, chalo, fine, thank you, bye bye.
Thank you, sir.